So I think we can start now. So can you hear me? Okay, so let me share my screen. Okay, can you see the screen? Okay, so first, just to remind you that the assignment 3 has been uploaded to Blackboard and is due next Tuesday. So about 1 week time. So remember to submit it on time. So in this exercise section, we will move on to another very important interactions in standard model, which is strong interactions between the quarks, and the quantum theory to describe the strong interaction is the quantum chromodynamics. And chromo means the color degree of freedom. And I think most of you know that why we need the color degree of freedom. And because in the quark model, if we don't have the color degree of freedom, that will contradict the Pauli exclusion principle. But I think most of you didn't know the details of it. So I would like to talk more on this before going to the exercise questions. So we can consider an examples. So let's consider these delta baryons. And from experiments, we know that the spin is 3/2. And from the quark model, we know that the composition is UUU. And we also know that it is at the ground state. So the ground state just means, so just like hydrogen atom, we have many states here, and this L is equals 0, is L equals 1. So the ground state is always L equals 0. And here, because we have 3 particles, so we have 2 angular momentum number. So the ground state means that they all to be 0. So that means the total state of the delta baryons can be written into 3 parts. So the first part is the spatial parts, which is the ground state. And the second part is the spin state. And here is how we add the angular momentum of 3 spin particles. So so it can be decomposed into the structure of 4 + 2 + 2. And because it is a spin 3/2 particles, so the only 4 spin states are this 4 spin states. So, and then we can consider flavor states. So similarly, for flavor symmetry, we use the SU3 group, and it can be decomposed into this structure. And because delta baryon have a quark composition of UUU, so the flavor state is here. And then we find that if we just include these 3 parts, the total state will be symmetric. So for the spatial state, because we are considering ground state, so the wave function is symmetric respect to the free quarks. And for the spin states, we can also see that it is symmetric. So for example, if we consider this spin state, if we exchange 1 and 2, or 2 and 3, or 1 and 3, you can see that we'll get back the same state. So the spin state is also symmetric. And the flavor state is also symmetric. So the total state will be symmetric. And this causes trouble because we know that for fermions, the wave function should be anti-symmetric. And that's why the quark model is contradictory to the Pauli exclusion principle. And to solve this trouble, people just introduce an additional degree of freedom, which is like color. And moreover, we require the color state to be anti-symmetric. And so the total states will be anti-symmetric, and this solves the troubles. And to be anti-symmetric, the color state should be a color singlet. And that's why we postulate that all the observable particles should be colorless. So that's just some additional information for you to know why we introduced the color of quarks. And if you want to know more about this, you can read chapter 5 of the Griffith textbook. And in this course, we have skipped this chapter, but I think it's very useful for you to read this chapter by yourself. So in summary, for the quarks, we have 3 symmetry correspond to the 3 degree of freedom. So we have the SU2 rotational symmetries, and this will give rise to the spin degree of freedom. And we also have the SU3 flavor symmetries, which will give rise to the flavor degree of freedom. And lastly, we have the color symmetry, which will give rise to the color degree of freedom of the quarks. And so let's move on to discuss the exercise questions. So the first question asks us to find the color factor of this diagram. So we have to find the amplitude of this diagram. So we just follow the Feynman rules. And here are the components of the externalized vertexes and the propagators. And you just follow the steps. So the first step is to follow the fermion lines in backward directions. So for example, we can consider this. And so we first write down the factor for this external line. And then we have a vertex vector. And then we write down the vector of this external line. And similarly, we follow backward, and then we can write down the three factors here. And lastly, we write down the propagators in the middle. And remember, don't forget to change the indices here, because these indices will be contracted with the indices here. So don't just copy the previous part. Okay, and the second step is to consider the energy momentum conservation at each vertex and integration and integrate the expression over the internal momentum Q. So here's the two conservations of these two vertex, and we integrate it over Q. And to do this, we just replace the Q by P1 plus P2 or P3 plus P4. It doesn't matter. So here we just replace it by P1 plus P2. And then lastly, we cancel this factor and multiply the whole expression by I. And we can get the final expression of the probability amplitude. And then we can further simplify it. First, we can contract this new indices. So can just pull down this new to the lower indices, and also you can contract this alpha beta. So you just replace the beta by the alpha, and then we can separate out the color degree of freedom. So the previous part is what we get if we don't consider color, and this is the additional factor that we will get if we consider color. And so this is the color factor. Okay, so let's go to the second part. So for B part, we want to evaluate this color factor by imposing some explicit color configuration. So here we are asked to find the color factor when the two incoming quarks are in color singlet configurations. So to deal with superposition states, what we have to do is to list out all the possibilities and then add them up. So so here we have 9 possibilities. So we can have R bar to R bar, R bar to PB bar, and etc. So we have 9 possibilities. And here also in square root 3 to keep track with the normalization factor. So we can first consider this. So here we have R bar to R bar. So this R bar to R bar. So we can first consider C1, C2. So C1, C2. And they are both red. So we can just put down 100 here. And also the normalization factor. And then we can put in C1, C3, C4. So C3, C4 is also red. So we also put down 100 here. So this is the term for the first for this. And we can do the similar things for the remaining terms. So for example, for this one, C1, C2 will be red, and C3, C4 will be blue. So we just for blue we just put down 0, 1, 0. And so we have we just have to add these 9 terms. And here we can see that. Okay. Oh, okay. Just first, this lambda is a 3 times 3 matrix. And so this whole expression is just equivalent to lambda 1, 1, which is the top left element. And for example, here you can see that this is just equivalent to the 2, 2 element of the lambda matrix. And so we can further simplify the color factor into this. And we can further simplify by grouping the terms. And then we have to do the summation over the repeated indices. So here, alpha will just go from 1 to x, because we have x get 1 matrices. So there's a hidden summation sign here. So we can consider the explicit form of these X matrices. So for example, for this for this term. We just have to add up the squares of lambda 1, 1. So it's just 0 plus 0 plus 1 plus 0 plus 0 plus 0 plus 0 plus 1 over 3. And similarly for lambda 2, 2 is 0, 0, 1, 0, 0, 0, 0, 1 third, etc. So we can just write down all the terms here. And finally, we can find that the color factor is 0. And in your textbook, it has an alternative method. Not really an alternative, but it's just a faster calculation method. So we can rewrite the following, the previous summation into the product of these square brackets. So if you expand it, you will find that it's actually the same expression as what we write down just now. But here you can find that this is lambda 1, 1. This is lambda 2, 2. This is lambda 3, 3. And when they add up, they are just the trace of the lambda matrices. So the whole expression can be written into the product of the trace. And you will see that all the gamma matrix, we have the trace 0. So the whole expression is again 0. So this is just a faster method. Yes, you're right. We assume the output is also color singlet because color is conserved in strong interactions. Okay, so the color factor is 0, and it just means that the whole amplitude is 0 for this diagram if we impose the color singlet initial conditions. So it just means that a color singlet cannot couple with the gluon in this way. So let's move on to the second question. So the second question is again asks us to find the color factor. And here's the expression for this diagram. So for the first case, we consider BG bar. So it's not a superposition, so it's quite straightforward. So we just this is B, this is G bar, this B, this G bar. So C1 is blue, and C2 is green, and C3 is blue, and C4 is green. So we just substitute the corresponding column factors. And so is this the result. And then we substitute the values. So here is lambda 22 multiplied by lambda 33. So we just multiply these two elements. So it's 0, 0, 0, 0, 0, 0, 0, and then 2/3 minus 2/3. So the final result is minus 1/6. Okay, and then for the second case, we want to calculate for R bar minus PP bar over square root 2. And similar to what we have done in question 1, we can list out these 4 possibilities. So we can first consider the first case. So here is our bar, our bar. And so C1, C2 will be red. And be careful that here C1, C2 is in the middle. While in question 1, C1, C2 is all in these brackets. So and then for C3, C4 is also red. So we can put down 1, 0, 0. And so we can put down all the terms. And similarly, we can get this result. And we use the Galvan matrices to calculate the sum. And finally, we can get minus 1/6. Okay, I think that's all for today. can ask question if you are confused, and if not, you can leave now. Why the two red quarks can be two blue quarks in Q1b? Okay, let me see. So why the two red quarks? So what do you mean by two red quarks can be two blue quarks? The gluon should carry out the color difference. Yeah, you can consider it this way. Let me see. So suppose this spread. Right. Carry out the color difference. Yeah, that's another way to think that why the color factor is 0 here. Because if we analyze the flow of the color, you will see that the gluon cannot carry away the color difference. Yeah, we have to include all the possibilities, and calculation. But in calculations, we just in a calculation, we usually don't look into the flow of the colors and just blindly apply substitute it into the amplitude, and finally when we add them up, you can see that the factor is 0, and it actually is actually saying that it's impossible for this color process to happen. So it's true that gluon can have color state that are superposition of RBG. Gluon is a color octet. So I don't know if Professor mentioned we have 3 times 3 equals x plus 1. So a gluon is a color octet, and that's what our conclusion. And a color singlet cannot couple with a color octet. because if our bar can transit to our bar, then the gluon will be colorless, and that's not possible. Okay. Okay. Any other questions? Okay. So see you next week. Okay. Goodbye.